next paper is by Ms. Rubel. Hope I'm pronouncing the name right. She's a senior chemist and also a manager of thermal analysis and mass spectrometry at the Center for Applied Energy Research. She earned her Master's of Science degree in chemistry at the University of Illinois at Champaign, Illinois, and her Bachelor of Arts in Chemistry at Washington University in St. Louis. She has over 50 publications in the area of oil shale processing and NOx flue gas emissions control. And her current interest is the use of activated carbons for NOx flue gas emissions control. Today she's going to speak to us on absorption and NO conversion on activated carbons. Ms. Rubel.
Thank you. First pointer. Then leave.
Nice job. It didn't work.
Thank you. Thank you. Well, I'd like to thank everybody that's in the room for staying till the bitter end. I'd like to acknowledge my co-authors here, Mark Stewart and John Stenzel. And before I get into the bulk of my presentation, I'd like to address at least one question as to why to study NOx adsorption onto activated carbons. I think as everyone in this room knows, NOx is an important atmospheric pollutant. It is, has been implicated in acid precipitation, in ground level ozone formation, and in haze production. And the 1990 Clean Air Act has set a timetable for its regulation and control. A process developed which would selectively capture NOx from combustion flue gas without the addition of any other chemicals would be a chemically benign process, and therefore our interest in looking at NOx absorption on activated carbons. I would also like to acknowledge the support for this work by the University of Kentucky Center for Applied Energy Research. In terms of the outline for my presentation, I basically am going to start by giving you a list of what we have studied in the area of NOx adsorption onto activated carbons. I will give our experimental plan, including the materials that we've studied, the adsorption capacity determinations that we use at the University of Kentucky Center for Applied Energy Research, and I will discuss the analytical procedures that were used to characterize the carbons that we used. I will then go into my results, which I've divided into two sections. The first, I will discuss what we know about the chemistry of NOx adsorption. During this part, I will discuss the differences between NO and NO2 adsorption onto activated carbons, and I will try to conclude this section with proposing a mechanism of adsorption. Then the next section and the results will deal with a study that we did looking at the chemical and physical properties of different carbons and trying to relate those properties to their adsorption capacities. And I will then conclude. In terms of what we have studied at the center in terms of NOx absorption, in simulated combustion flue gases, we have looked at basically the temperature of adsorption. We have tried to look at the capacities of carbons for NO, the effect of repeated adsorption and desorption cycles on the adsorption capacities. We have looked at the effects of pretreatment temperatures and atmospheres. We have tried to determine the percent of NO that was chemisorbed versus physisorbed onto the carbon, and we have looked at the effect of water vapor on adsorption. We have also done a study looking at the differences in the chemistry and kinetics of NO versus NO2 absorption. And in this area, we tried to identify the desorbed oxide. We looked at the effects and role of CO2 and oxygen, which are important components of combustion flue gas. We have looked at the differences in the rates of absorption. We have determined the heats of absorption, and we then have used these differences between NO and NO2 absorption and desorption to try to better understand the mechanisms. We'll now go into our experimental section. Basically, our experimental plan was to look at NO adsorption under typical flue gas or combustion flue gas conditions, both in terms of gas concentrations and in terms of temperature. Now, when we started this project, there was a lot of information available in the literature on NO adsorption onto activated carbons, but we couldn't find anything dealing with that adsorption under conditions which you would find typical of a combustion flue gas stack. And so that was our plan when we set out. So what did we look at in terms of materials? First of all, we chose 4 commercially available carbons. 2 of them were coal-based carbons. We chose a coconut-based carbon and a petroleum pitch carbon fiber. The concentration of flue gas that we used is shown here. The concentrations that we most often used are indicated first. We used 2% NO or NO2 in our gas, 5% oxygen, 15% CO2, and usually 0.4% water. But we have looked at the ranges that are also indicated in parentheses, and we do use helium as our makeup gas. Now this next view graph is really results, but it is good here because it shows why we chose the 4 carbons that we studied. Basically, again, we wanted to look at carbons from different sources. I will, in later results, identify these carbons by these letters. But in general, the adsorption of compounds onto a carbon is related to the carbon's surface area. And so we wanted to look at a wide range of surface areas. And you can see we go here from 460 meters per gram to 2,000. Additionally, if you look here at the void or the pore volumes, we had a pore volume from 0.3 to about 0.9. Pore volumes did not relate to surface area. In terms of this carbon here with the lowest surface area had the second highest pore volume and actually the highest mesopore volume. Now, to look at how we determined adsorption capacity of the carbons. The method that we used at the center is by utilizing a TG mass spec system that we have. We have a thermogravimetric analyzer that is coupled to a quadrupole mass spec, which allows us to determine weight gains and losses during adsorption, desorption, and coupling that with mass spec identification of the desorbed gases. The conditions that we use during this test is normally we have a carbon sample weight of 20 milligrams. Again, here I put the most commonly used conditions first with the range of conditions that we've studied afterwards. Most of the time we use 20 mils per minute bypass gas flow. This is monitored at room temperature and pressure. Adsorption temperature that has been studied the most is 70 degrees C. Adsorption time of 30 minutes, although we have looked at from 30 minutes to 3 hours. Maximum desorption temperature, normally 200. We've gone up to 9. And the desorption heating rate from 20, usually 20 degrees C per minute. And basically that's as fast as our one of our units will heat up. that system. Basically what we have is a thermal analyzer which is coupled via a fused silica capillary transfer line, which takes a small sample from the vicinity of the sample pans in the TG and transfers it to a metrocell molecular leaf, which interfaces the capillary with the analysis chamber of the mass spec. Both of these units are controlled by dedicated computers, which also can communicate with each other. And in general, we transfer the data to floppy disk and then take it into a spreadsheet for data integration and analysis. Now, the carbons that we studied were submitted to the following analytical determinations. We did proximate analysis, ultimate analysis, pH, we determined the pH of the carbons, and we did surface area and pore volumes by mercury fluorosimetry and nitrogen VET surface area determinations. Now to go into our results. Basically, the first part of these results will give you what we believe we know now about NOx adsorption under typical flue gas conditions. I will give a comparison of NO versus NO2, and then try to put this all together in some sort of mechanism of adsorption. But first of all, I would like to show you the type of data we get off of our TGMS system. I refer to these as adsorption, desorption profiles, and these are really the backbone of our results, these analytical determinations. This is a single cycle adsorption, desorption profile showing the integrated data from our TG mass spec. And basically, the yellow line is the temperature profile. The green line is the weight loss or weight gain, weight loss curve. And the red line is the mass spectra for mass 30, which is the major mass ion for both NO and NO2. We do accumulate from 1 to 100 atomic mass units on our mass spectra. So we do know whether, what gases are involved, if there are other gases other than a nitrogen oxide. Basically, our procedure is to heat the sample up in a preconditioning step to the maximum temperature that we're going to use during desorption. This will remove, as you see here by a slight weight loss, any pre-adsorbed gases on the carbon. The sample is then cooled to the desired adsorption temperature, which in this case was 70 degrees C. The simulated flue gas is turned on. In this case, it had this concentration. And the sample is allowed to become saturated with the adsorbate, at which point the simulated flue gas is turned off and we purge the system with an inert gas. The weight loss during that time is related to physically adsorbed materials. We then go through a temperature program desorption step, and as you see here, we get a very nice peak mass 30. We also get a small peak at mass 46, and the ion ratio, 30 to 46, indicates that we have NO2 being evolved from this carbon, and we do not see any other gas species evolved during this temperature program desorption step. What this type of data has showed us is that we can adsorb. This is an adsorption of nearly 15% of the carbon at a temperature that's consistent with what you would find in a flue gas stack. Additionally, the temperature at which desorption occurs, this was 140 degrees C, is significantly removed from the adsorption temperature that we could then desorb a concentrated stream of NO2 away from the stack. The desorption temperature is also significantly below carbon gasification temperatures, so that you would not have a problem with loss of carbon to gasification. And we can use this type of profiles in a repeated mode. As you see here, This is a 3-cycle adsorption desorption profile. Under the same conditions of the previous slide, we use this to see if repeated cycling will cause deterioration of adsorption capacity. And as you can see, there's a bit of a loss from 1 to 2% of adsorption capacity, which can be partially attributed to about a 1% loss if you follow the black line in the weight of the carbon. Subsequent to this work, we have considerably lowered the desorption temperature. We now find that since the maximum desorption temperature is about 140 degrees C, we only routinely go up to 200 degrees C, minimize this loss here, and additionally minimize an already small loss in adsorption capacity. Now, we did a fairly extensive study looking at the differences between the adsorption of NO and NO2 onto activated carbons. We wanted to particularly look at the effects of other combustion gases. And so we looked at the adsorption of both NO and NO2 in various combinations of CO2 and oxygen. Additionally, we have 2 cases here where we looked at pre-saturating the carbon with CO2 and then doing adsorption in helium, and pre-saturating with oxygen and then adsorption in helium. What's plotted here is the relative adsorption relative to the base case. We've taken this as the base case where we have both CO2 and oxygen present. And what's immediately obvious here is that for NO2, oxygen is required, and CO2 does not appear to be detrimental to the reaction. If you look here at the very little adsorption that you see with NO and helium, this is really what the information that we found in the literature before we started this study. Very low levels of adsorption of NO, and the significance of this work is the fact that when you have oxygen present, you get a significant increase in the level of NO adsorption onto activated carbons. This case here where we pre-saturated with oxygen and we get much better adsorption from the base case, we're not really sure. There's about a 0.5% increase in weight of the carbon with the pre-saturation of oxygen. However, it's very difficult to purge this rather large system of oxygen completely before adsorption. So it may be due to slightly higher levels of oxygen present at the beginning of the adsorption rate. Now, if you look at the situation with NO2, adsorption occurs irregardless of whether you have oxygen present or not. Adsorption in helium alone is only very slightly less than when oxygen is present. Now the control runs for that previous slide is shown here, basically looking at if there was any significant amount of oxygen, helium, CO2, or water that was absorbed onto the carbon. And this is the base case here where you have nitrogen oxide, CO2, and oxygen. And as you see, we get nearly 12.5% adsorption. And the highest of these is CO2, which is less than 1.5%, or about 1.5%. The effect of water vapor. Water vapor is a very important part of combustion flue gas. You can see here we have 2 concentrations of water vapor in the simulated flue gas, 0.4 to 0.6. This nearly 15-fold increase in moisture only slightly decreased the adsorption capacity of the carbon. Now to look at the rates, the differences in the rates of adsorption between NO and NO2. For this series of experiments, we did 3 experiments eliminating CO2 from the combustion flue gas. We were fairly confident at this stage that CO2 does not either interfere or participate in the reaction. And it simplifies the mass spectrum by eliminating it from the experiment. And so we did 3 very comparable experiments where we looked at the adsorption of NO in oxygen, balanced helium, NO2, O2 and helium, and NO2 and helium. And as you can see, in terms of the rates of the reaction, after a very short 5-minute lag period, the initial rate of NO and oxygen, the initial rate of uptake is faster than for the NO2 case. And for NO2 and helium, that reaction rate is a little bit slower all the way through, and additionally there's slightly less nitrogen oxide absorbed. We took this to imply that even in the case of NO2 and oxygen, there must be some interaction between the carbon and the oxygen that affects the rate of the reaction. Our TGA does simultaneous differential thermal analysis, and that is what's plotted on this slide, or this view graph. And as you can see, quite interestingly, in all 3 cases we get an exotherm. For the case of nitrogen oxide in oxygen, we get a significant exotherm, and integrating under these curves allows us to determine the heats of adsorption, which is what is shown on the next slide. And as you can see here, the heat of adsorption, when calculated for the NO and oxygen case, implies that we have the reverse of this reaction occurring, that nitrogen oxide plus oxygen is being converted to NO2. In order for this to be determined by our system, this must be occurring at the surface of the carbon. So what do we know about a possible mechanism, or what can we say about a possible mechanism of adsorption? First of all, we know that oxygen is a requirement, that it appears that this is a surface reaction because we would not be able to determine the heats of adsorption otherwise, and the evolved species that has been identified is nitrogen dioxide. And we believe that this must be a catalytic conversion at the surface of the carbon. All those factors imply that there is an interaction between nitrogen oxide and oxygen and the surface of the carbon, which we have shown here as these yellow dashed lines. Whether this actually means that those species are weakly chemically bound to the carbon or merely associated in some way, we're not really sure. However, what we can say is that in other systems, for instance, in the Mordenite system, an NO plus ion has been identified as stable. NO plus ion has been identified by FTIR. And so what we would like to propose is the formation of ion pairs as a possible mechanism. Additionally, in the Mordenite system, this NO plus has been related to the conversion of NO to NO2. Additionally, the electron affinity of both NO2 and oxygen would favor the formation of this NO2 minus or O2 minus species. Both the O2 minus and O minus are known to exist, and therefore we would like to propose a mechanism whereby basically both of those negative ions are involved with the addition of more nitrogen oxide to produce NO2. Now, whether this NO2 remains bound in some way, weakly bound in some way to the carbon, or merely occupies the void space in the pores of the carbon, we really can't say right now, although our most recent evidence seems to indicate that it just resides within the pores of the carbon. Now, I'd like to summarize before going on to the second part my results. I'd sort of like to summarize this section. First of all, we have found that NOx absorption onto activated carbons is rapid and selective in the presence of oxygen, CO2, and water. Nitrogen oxide adsorption requires oxygen. NO2 occurs with or without the presence of oxygen. CO2 and water do not inhibit adsorption. Oxygen, CO2, and water are not themselves significantly adsorbed. On heating, NO2 is desorbed at about 138 to 140 C. You can do many adsorption-desorption cycles with the same carbon. The heat of adsorption indicates that NO in the presence of oxygen is converted to NO2. A few mistakes with that line. And the data also suggests that there is a diffusion control element to NOx adsorption onto activated carbons. Now the second part of our results section, any process that would be developed using activated carbons for the adsorption of NOx would require that we obtain a carbon with very high adsorption capacity. And therefore, we wanted to look at some chemical and physical properties of carbons and try to relate those to adsorption capacity. And I showed you the physical properties of some of these carbons in the table before. But now let's look at their adsorption capacity. Basically, we had absorption capacities which varied from 11 weight percent of the carbon to 15 weight percent of the carbon. And interesting enough, both carbons A and C were coal-based carbons, and their adsorption capacities varied sort of opposite of what you would expect from surface area measurements. The surface area of this carbon C, which really was the worst carbon, or had the worst adsorption capacity, was half of the BET surface area of carbon A. Looking at adsorption rates, the adsorption rates also vary twofold, going from 0.33 millimoles of NO2 per gram of carbon per minute to 0.67. And actually one of the better correlations, we did linear correlations with all these properties. One of the better correlations that we obtained during the study was the correlation between adsorption capacity and the maximum rate of adsorption. You can see here this is a coefficient of determination of 0.91. Desorption rates were very similar for all the carbons, varying only from 0.28 to about 0.36, I believe, millimoles of NO2 per gram of carbon per minute. And then, like I said, we did linear correlations between all the chemical and physical properties that we studied with both adsorption capacity and adsorption rate. But since adsorption capacity and rate were related, they were very similar. So I'm just going to show you adsorption capacity. And as you can see here, these are the physical properties. Really, there wasn't any good correlation. The best was an inverse correlation with mesopore surface area. But if you do notice, the two best performing carbons had very similar BET surface area determinations. They also had very similar micropore volumes, but were widely dispersed on total pore volume and mesopore volume. In terms of the chemical properties, looking at this is proximate analysis. We got this, the best correlation here was this with moisture. We think this is probably a fluke in that we have taken this carbon A, completely saturated it with water, or basically mixed it with water, filtered out the water, and wet have done another adsorption test and gotten the same results. So we feel that there's some other property here that also affects moisture that is causing this this correlation. Otherwise, the two good performing carbons did have very similar proximate analyses. In terms of looking at the elemental analysis and the pH, again, no significant correlations. However, the two good carbons did have similar carbon content, nitrogen and oxygen by difference, but were widely different in the other three parameters measured. The other thing that we looked at was pore size distribution, and as you see here, the two high-capacity carbons had very similar pore size distribution. Additionally, they had slightly lower effective pore diameters. These distributions were relatively narrow with slightly lower effective pore diameters. And when we did the correlation of this view graph here shows maximum adsorption rate versus effective pore diameter, we got really one of the better correlations that we obtained during the study. Now to summarize this section. Basically, of the 4 carbons that we studied, we saw adsorption capacities of from 0.11 to 0.15 grams of NO2 per gram of carbon. Adsorption rates varied from 0.33 to 0.65 millimoles of NO2 per gram of carbon per minute. The adsorption capacities increased with adsorption rate. Desorption rates were very similar, and we really found no correlations between the carbon properties studied and adsorption capacity. However, high capacity carbons did have some similar properties, and the best correlation was between rate and effective pore diameters. And so to conclude, basically, NOx adsorption onto activated carbons can be rapid and selective in the presence of oxygen, CO2, and water. It involves the catalytic conversion of NO plus oxygen to NO2 at the surface of the carbon. And an important characteristic of the carbon that would be used for a process would possibly contain a narrow pore size distribution around an optimum effective pore diameter. Thank you very much. Yes?
How are these materials
Basically, just heating them up to 200 degrees.
But then you reverse what you tried to accomplish.
Basically, that one, well, no, what you're trying to accomplish is to remove the NOx from the combustion stack and possibly then concentrating it on a separate stream, which could be dealt with, like, say, for chemical utilization, for production of nitric acid.
So it would require some kind of further processing.
Right. Well, it could be used, we've investigated the possibility of using it, like I say, for nitric acid production or fertilizers, that sort of thing. It would be a separate chemical, basically, concentrating a chemical that may be of some economic value.
What would SO2 or SOx do?
We have not investigated, this is the recycling, we have not investigated the effects of SO2 on this process. This, as it is right now, would work as a post-SO2 cleanup situation. We do plan on looking at SO2, the effects of SO2 on this.
These are what's, I guess, for want of a better term, one would call equilibrium capacities. Do you have any idea what a working capacity would be at the contact time one would find in a flue gas stream?
We have done those calculations, and in fact, we're way, I believe, John, isn't this right? We're way above those contact times in terms of our experimental apparatus.
Yeah, well, in terms of NO flow rates, yeah, mass flow rates of NO. But in terms of the contact time, we haven't looked at that very closely.
How many cycles did you take any given sample to just to see how it spins after cycling? I mean, 3 cycles is not that many as you show.
Right, well, I showed 3 here, but in fact, since then, I've gone, I'm really not sure, but multiple cycles. In fact, we have a high-pressure unit where I can load a sample, and basically we just keep using it, you know, and eventually just, for sake of nothing else, maybe starting a new series of experiments, I'll change the carbon sample. But we have gone certainly a dozen or more cycles.
I go through the difference between the different carbons you looked at in absorption capacity very large. The difference being very large. And I would have expected some correlation with the type of mineral matter you would have in those carbons. So you show the ash content but not the composition of the ash.
Right.
Did you look at that?
No, we haven't. And that is one thing that we hope to look at, especially the effect of ash content. Yeah, but we have not.
Also the type of mineral.
Right, the type of, no, we have not done that. Okay.
Thank you very much.